Hi, my name is Zaid Anwar, and I go to university schools in Cleveland, Ohio. My project that I'm presenting today aimed to study the characteristics of internally generated movements studied through eye movement patterns in patients with Parkinson's disease. So, let me just kind of give you some background information on that. So, what is Parkinson's disease? Parkinson's is a neurodegenerative disorder in which 1 out of 100 patients over 60 are affected with Parkinson's disease. Not only that, but it is gone very close to me personally because my uncle from Pakistan suffers from Parkinson's disease and has a lot of mobility issues that come from Parkinson's disease and all of the symptoms that come along with it. It impairs your motor control of your actual limbs and body, but also your fine motor control with when you're writing or moving your eyes, and affects your both voluntary movements and reflective movements. So even if you just reflex or like not even trying to move, it might affect those movements as well. And I am studying these external versus internally generated movements and decremental patterns. So I'll first explain what external and internal generated movements are. Externally generated movements are cue-based movements. I'll get to this later, but if I tell the patient with Parkinson's to look between two individual points, that is an external movement where I am telling them to look left, right, left, right. And that is an external movement, while an internal movement is where they are looking at their own pace. So I would just be telling them to look left and right, and they would be doing this, something sort of along like that. And decremental patterns is seen a lot of the time in Parkinson's and is not a very studied point of Parkinson's. These decremental patterns, again, I'll get to this later, but this is when they are looking between 2 points. And when they look between a point, they might look here, but then the steps, it gets a little bit smaller until they're not looking at the 2 points. They're looking in between it, and it gets smaller and smaller over time. This is seen not only through the eye, but also through the legs, their movement steps. When they're stepping, they'll take a long step and a shorter one, shorter one, shorter one, and they'll have to reset, recenter, catch their breath, and then start taking another step. And it's very hard, and also makes falls very prevalent, and that's why it's such a big problem, and that's why I really want to start. So the reason I kind of like chose Parkinson's in the first place, my uncle from Pakistan, he had Parkinson's, and I would always visit Pakistan to see my family over the summer. And whenever I saw him, I was always curious, even from a young age, on why my family was so protective over him, or why they were so scared of him, and what was kind of like wrong as so much with him, even though there's nothing wrong with that. And I was always curious about it, so I knew I wanted to do this project on Parkinson's. So the research goals of my project was to kind of study how disorders of the basal ganglia, these are structures within the human brain, alter internally generated movements. This is studied through the eye model because these eye models are the best way to actually collect data objectively. Like if I were to collect data with, your step length, how do you objectify that? Or if I do your handwriting length, how do you kind of like make solid numbers with that? However, with eye movements, you can actually get, the amplitude of the eyes, the speed of the eyes, the velocity, irregularity, the volume of the eyes. There's a lot of factors that you can control. And what I hypothesized based on previous literature, using, steps from incrementally slower times initiation. I got this from their steps where they're taking a slower time to actually start their step, reduced velocity, so they're going slower, decreased amplitude. That's your decremental movement that's seen a lot, but it hasn't really seen the characteristics of these decremental patterns. It's only seen that there is one, and that's what I really wanted to study. And increased irregularity. So they'll start from here and then maybe like go here and then wait a little bit and go over there. So it's a lot of irregular timing and all of that. And when these external cues are provided, it'll become more controlled. That was my research goal. So the way I kind of study this, so I first reach out to a lot of labs, and what I found was that most labs wouldn't allow me to, get these hands-on experience that I kind of wanted to kind of do my own project. So I knew I wanted to take a step back and kind of ask them if I could, use their facilities, maybe have some of their mentoring, but do my own project. And I was very fortunate to have Cleveland Clinic and Dr. Asif Sheikh from Cleveland Clinic to allow me to use his facilities and do this work kind of myself with their mentoring and not be a part of their whole overall study. And that's what I did. So what I did was I recruited 10 Parkinson's patients from this lab. They were generous in providing me it and giving me their forms signed, and I asked also allowed them or asked them to sign some forms for me. And I set up an Apple iPhone software. This was developed by Case Western, and it is a cell phone app where it tracks, data and it tracks all of these types of uh, data that I will be showing you later. And I displayed two visual targets. The left one was blue and the right one was brown. And I told them to, for their external cues, I told them, brown, blue, brown, blue. And that was their cue-based kind of reactions. And when I told them to do the internal movements, I asked them to, look at between them as fast as you can. And then after I collected these, I took out the key parameters like the amplitude, velocity, acceleration, deceleration, irregularity, and all of that good stuff. And going on to some of my results, this is the first patient where you can see that it's very controlled, and you'll see this throughout all of the external movements. It's controlled. There's not that much irregularity. It's symmetrical. The top stay at the top, the low stay at the low. However, when you look to the internally generated movements, this is an example of the decrease in amplitude and their decremental pattern. So what you see is that it starts off higher, and they'll look left and right, and they'll go slowly left and then slowly right until they're looking between a very thin point while the circles are over here. And that was kind of interesting to see. And that was the amplitude that I kind of saw. On patient two, you can see in their internally generated movements that they're going a lot slower. Their speed and velocity is affected greatly. They can't do it fast enough. Remember, this is as fast as they can on their own pace. And we made sure that there's no fatigue or anything, and that's the fastest they can go while being controlled. And even though it might be having a little bit of highs and lows, there's like not at all a lot of like speed or velocity in this kind of drawing. And then in patient three, there was a decrease in timing and irregularity. So what that kind of means is that these patient three, he had kind of pretty controlled in external general movements, but when he goes to internal general movements, when he looks from left to right to left to right, when he looks to left to right, he'll maybe look left, wait a few seconds, look right, immediately look left. This timing is all messed up when it's not supposed to be, or he's not trying to do it like that. And then finally, patient four, all the other, symptoms were kind of expected. I had them on my hypothesis. Patient four was a little bit different. I did not have this on my hypothesis, but now that I look at it, it kind of makes sense. This is where they are having differences in the cross X or their trajectory, where they're looking left and then right, or maybe and then maybe top left and then bottom right, where they're not trying to do this, but that's what the Parkinson's neurodegenerative disorder is making them do. And that is really crucial because, if they're trying to take a step and they can't put their foot where they want it to go, that could be very dangerous, cause a lot of falls. So that was what I found in my data. And if you look to control patients, it's pretty same throughout. It's controlled on the top, controlled on the bottom. Um, it's a little bit different here. These are the external moves where they're kind of the same. They're all the same, and then there's no discrepancies in here. There's no discrepancies. They're pretty much the same. So some of the conclusions we can draw on this is that right now with our PD stations, there's impairments in amplitude, velocity, timing, and trajectory. With our healthy volunteers, as expected, there's no really differences. And this kind of suggests that Parkinson's patients rely heavily on external cues for eye movements. It supported my hypothesis, and it really kind of emphasizes the role of actual externally stimulating these Parkinson's patients' movements and future directions of where I want this to go. I kind of want this project to go to exploring kind of like ways to use this cue-based movements or like actual movements in order for them to rehabilitate more. But I also think one major very good way in order to use this kind of information is to kind of use this to detect Parkinson's, because Parkinson's is very similar to Alzheimer's or ALS, and when you're trying to detect these neurodegenerative disorders, but this decremental pattern and what you see here in my data, this is not as much seen with these other diseases that are neurodegenerative order that are commonly misdiagnosed with Parkinson's. So you can use that, but you can also use it to do a biomarker on how much of their severity is their Parkinson's, at what stages they're at. And these are not abrasive methods. We're doing is recording their eye movements. Right now, the movements or the way they calculate what stage severity on, they're very abrasive. There's a lot of t vigorous testing, very exhausting for Parkinson's patients, and also keep in mind, very expensive. I know my uncle in Pakistan, he can't go to a lot of these, very daily or like, weekly type of meetings with their doctor to like develop or kind of help Parkinson's because it's just so expensive. And that's what I really kind of want to help and want this project to do. And you can also, use an AI to kind of examine these data, and maybe you can use the AI to kind of predict where the severity is at. So you don't even have to send it to a doctor, just have an AI do it and give it right there to the, patient who, doesn't have to go through a doctor, doesn't have to pay the doctor. They can just use an app. And that's what I really think is a lot of good, of many good applications of what I can do with this project and why I'm really passionate about it. So some of my acknowledgments, I really want to thank my PI, Dr. Asif Sheikh. He really was generous in allowing me to use his facilities while not being a part of his lab and making my project my own and kind of like mentoring me through that. I'm really thankful to him. My gratitude goes throughout to my patients, my volunteers, some of the lab staff that mentored me. I also want to extend my gratitude to Miss Winovich, Dr. Logs. Um, I also I have a little mistake over here, but I also just want to thank you for all you do in helping judging this Science Day competition and helping the day run smoothly and doing all of that. And here are some of my references. Thank you for listening to me. I hope you didn't get bored, and I hope you're, maybe see a lot more uses in my project and maybe become a lot more passionate like I am on Parkinson's and what we can do to really help people who don't have as much money, like my uncle in Pakistan. Um, and I hope you are healthy and have a good day. Thank you.